So we said that the net force matrix, which was going to be or net force vector, I'm sorry. This vector was going to be a 2 by 1, right? It was going to be my net force in, remember, net forces are on the masses, not on the springs, right? We do have net force analysis in the springs. This thing right here, we're going to give a special name, and we'll do that in just a second. We're going to call y of t is going to be the net force having to do with the internal spring constant. You might ask why, and I would say in this is one case where I'm going to ask you to swallow a bit of notation that is not intuitive to begin with, but is going to show up in other contexts in engineering if we go on in this space. If you go on in vibrations, if you go on in finite analysis, if you go on in finite element analysis, finite different analysis, there's a lot of places that this particular this thing shows up. Strang has a great book on this that's called Applied Mathematics. And so I'm using that notation so that we can prep ourselves for that. So from that standpoint, what is this particular vector? Well, this would be negative y of t plus f sub e of t, which is the force vector there, right? I think I want a negative there. Okay, so what was the net force on every single one of these? It's been a while since I did. I usually have them memorized, right? It's been a few years. What was the net force on each? How do we express that? It was going to be my internal force of my system plus my external force. Well, what was my internal force of my system? It was negative A transpose times my forces having to do with my springs, right? Plus Fe of t. Okay, what about the spring force right over there? What's that? This vector right here, I can write as a matrix vector product. Which one? It's right there. C times E of t. This thing right here, how can I write it? Yeah, what up? How can I write this thing right here? It's right up there. How did I write the elongation matrix? It was my matrix A times the vector U of t. Anybody wanting to reassess whether or not this class is easy? Many people say that to me at the first few weeks. Cute. We're going to call this thing right here K. That's called the stiffness matrix. So now we have that the net force vector on each of my masses, how big is that vector? It's 2 by 1. How big is the force of external forces, the vector of external forces on each mass? 2 by 1, because there's two masses, right? How big is the displacement? How many displacements are we measuring? 2 by 1. This matrix, go ahead and look at it up there. How big is the matrix A? 3 by 2. How big is the matrix C? 3 by 3. How big is the matrix A? Transpose. 2 by 3, 3 by 3, 3 by 3, 3 by 2, 2 by 1. So what's the output there? 2 by 1. Can I add a 2 by 1 by a 2 by 1? How big is K? If I call this thing K, how big is it? 2 by 2. So now I know my net force is going to be K times my displacement vector with a negative out front, plus my external force vector. But what else do I know about net forces? What did Newton's second law say? That if I want to find the net force, that wasn't just in my head, right? What's the net force on mass 1? It must be m1 times the acceleration of mass 1, where the dot notation comes from the second derivative. This is very much something that comes from engineering. So u double dot with the two dots on top means the second derivative of u with respect to t. The net force on mass 1 is mass 1 times the second derivative of displacement. In other words, what's this called? Newton's second law. What's the net force on mass 2? It would be m2 times the second derivative of mass 2. So u double dot, u2 double dot is the second derivative with respect to t of the displacement function. I'm going to go ahead and do something crazy. And you'd be like, you be doing crazy shit all day. I'll be like, chia. Anybody see a linear combination there? What's the linear combination? Should we break it up into pieces since we're doing our what we call a training mechanism? m1 u1 of t 0 plus 0 m2, and of course that would be the second derivative, right? So the net force vector, when I'm thinking about the net force on mass 1, and then also I have the net force on mass 2. These are functions, right? Because that's at any one point. Do you see a scalar multiple times a column? It's the acceleration of mass 1 multiplied by that column. What about this one? Multiplied by this column. Do you see a matrix vector product? Let's see. What's a matrix vector product from the standpoint of columns? Remember, scalar versions of matrix multiplication is really nice when you're constructing models. The column version is nice when you're doing mathematical analysis. We've already done the model, right? So now we're trying to analyze that model using matrices. Question? Move it over? Oh, lower it. Yeah, sorry. I can also raise it too. And the net elongation, no, sorry. Stop making math come alive, man. God damn it. What's this now? Why don't we call this whole thing, we'll call it the mass matrix. How big is it? 2 by 2. Why don't we call this the second derivative of the displacement vector? And that would be a 2 by 1, right? So what does that mean? Well, it means that the net force was equal to this, right? But the net force is also equal to this. That immediately implies that m times the second derivative of my displacement vector would be the negative spring constant times my displacement vector plus the vector of external forces. What do you know about subtraction? If I wanted to bring this over to the other side, what would you do? And those of you that have taken Math 2A will probably recognize this as a forced simple harmonic oscillator, except this is a coupled system. Right? You've seen this before if you've taken Math 2A. This is m u double dot with no damping coefficient equals f, right? No damping coefficient, except this is a 2 by 2 system, and this entire thing captures the dynamics of every single part of that system in one formula. This is going to be a source of an eigenvalue problem now. But let's forget about eigenvalues. Let's do linear systems, shall we? Do you have an external force vector? Okay. If we think back to T equals T with gravity on. What do you know about U double dot? What do you know so think about this for a second. Gravity's off, right? You can put gravity on. The things settle down to equilibrium in that second state, right? At T equals capital T seconds. What's the acceleration of those masses? 0. Ooh, exotic, blue. Since masses are at rest. And what's Fe of T? What's the external force vector? 9.8 times m1, 9.8 times m2. Whole idea is we have this matrix problem, m times u double dot of t plus k u of t equals Fe of t. What did we say about this? Goes to the 0 vector because there's no acceleration, which implies now I have k and perhaps you say at t equals capital T, time is a constant. So this is no longer a differential equation, it's what we call an algebraic equation. So we don't actually need to track the u's, the t's, do we? If you want to keep the little e to say that it's external force, that's cool. If I give you the measurements, what do we call that? Matrix vector multiplication problem. If I give you the masses, what do we call that? Linear systems problem. And in fact, not only is it a linear systems problem, it's a non-singular linear systems problem. This matrix, we will have a proof, this matrix is non-singular. In fact, it's called positive definite. Depending on which I asked you, usually I'm going to give you the masses, right? And then I'll say, predict for me the displacements. I have done this at home. Do you know what my intention for this class is? These videos are up. Before you ever walk in the door, you have to finish these videos, and then you take a quiz the first 15 minutes of class. And if you pass that quiz, then you'll actually be doing live demonstrations in class using that system. And you'll have to guess for yourself, using linear algebraic theory, how far the displacement of the masses are using a solution to a linear systems problem. And then you'll confirm or unconfirm whether or not the theory has any relevance to the real world problem by physically measuring displacements for different masses. I've got them to within a millimeter in the privacy of my own home.